Hello everyone, my name is Ian Stewart, and today I will be telling you about my honors capstone project, the Solar Array Analysis Suite, done in tandem with the University of Michigan Solar Car team and under the advisement of Professor Harvey Bell. So first, a bit of background information. As I mentioned, this project was done in service of the University of Michigan Solar Car team, where we design, build, and race some of the world's fastest solar-powered electric vehicles. Traditionally, the team travels to Australia to race in the World Solar Challenge every other year. However, the 2021 edition of the race was actually cancelled due to concerns with COVID-19, and so the team will instead be attempting an alternate event during the summer of 2022. Because this alternate event will have an even longer distance than usual, our array and solar cells will be even more important, as we will have more time on the road and will need to capture more energy from the sun to successfully complete the race. To give you an idea of what our cars might look like, here's two photos of our 2019 car, Electrum, which took third place in the 2019 Bridgestone World Solar Challenge. So first off, when designing a car, we normally have in the past done sort of hand calcs to determine what our array would actually bring in from the sun and then upgraded to spreadsheets. But really, the team needs a software package to rapidly prototype and analyze array designs much faster than those two methods that we've been using in the past can. A new software package should integrate directly with our current array design methods and include as many different sources of inefficiency as possible. It should also provide clear and intuitive data readouts to inform array design decisions. So my actual project, it consists of 4 MATLAB modules and 1 Unity executable. It integrates with Siemens Nx, our team's CAD tool, as well as the team's own data analysis tools used by our strategy division. It is able to analyze our array on a per cell basis and track thermal losses, curvature losses, shading losses, and losses to our maximum power point trackers. It tracks the total system efficiency and predicts power brought in by the array. So when looking at any sort of physical phenomena, you really want to start at a very basic level, and in this case, when trying to maximize the efficiency of an array, we have to understand where all of the energy is flowing as it comes into the solar car and leaves the solar car. And so you'll see on the left here, we have all of the sunlight incident on the car. And of that, there are 2 large chunks. One that goes to the bottom, which is our captured solar energy. That's what we actually convert into usable electricity. And the one that goes to the top. That's our solar panel nominal inefficiency. And what that is that is the actual amount of sunlight that our solar panels themselves, the actual cells, are incapable of absorbing, because they just aren't efficient enough at converting sunlight into electricity. However, you'll note there are also a lot of other little smaller bars coming off below the solar panel nominal inefficiency, as well as canopy shading losses at the very bottom of the page. And the idea of designing an array is to essentially minimize all of those different losses as much as you can to maximize the captured solar energy by the array. We can't really change the nominal inefficiency, short of spending more money on better cells, which isn't always an option. But designing your array and using good engineering practices can help to minimize your losses to other factors and maximize the amount of energy that the car gets to put down onto the road. So the actual process of using my software tools. First, the array is designed in Siemens Nx. You can see in the top photo there, we have a car aero body. That's the shape of the car. And on it, there are a bunch of blue squares, one for each individual solar cell. Once that has been created, the CAD files for the aero body and the array are then imported into MATLAB, which you can see in the top right corner, where now we have sort of the MATLAB graphs with the CAD loaded in and the array sort of put on top of it as now a bunch of black squares. We then analyze this file, and then you'll see in the middle there, we have a photo where we've gone ahead and we've stripped away sort of the actual CAD of the cells and replaced it with a normal vector and the 4 different points of the plane of best fit for each individual cell. And this allows us to get a very good idea of where exactly the cell is pointing which will come into play when we start determining how much sunlight the cell is actually receiving. And then all of that data is exported into Unity, which you can see at the bottom, where we use the ray tracing features of Unity to simulate different positions of the sun relative to the car. And then as you can see there, some of the cells in green are actually being shaded by the canopy as the sun is above and slightly to the left of the car. And so those cells which are in the shade are not actually getting sunlight and won't be producing any electricity. We can then take the data from Unity about which cells are going to be shaded for what sun positions and import that back into MATLAB and run that through along with a bunch of other data provided by the strategy division that predicts things such as the weather and the heading of the car over the course of a race, and then get out a time-based model of how efficient each of our different cells will be. For example, the graph on screen shows the losses of cell 209 over the course of a projected race. So when actually going through and doing all of this math, it's important to keep track of which losses we're actually considering. And in this case, we're paying attention to the base cell efficiency because that is by far the largest loss. But then also we're approximating our thermal losses by taking a weighted average of the amount of energy that is lost to the sort of temperature of the cells. They happen to become less efficient as their temperature increases. We're also going ahead and through our Unity ray tracing model, modeling the shading losses over the course of a race, as well as our cosine losses or curvature losses over the course of a race. As you may imagine, a solar panel needs to be pointing at the sun in order to generate any energy. And so any sort of deviation from pointing directly at the sun is going to decrease the amount of energy that the cell can turn into electricity. That is what our cosine losses are. And that is why, as you'll see on the next slide, we're losing a lot of power to cosine losses at the start and end of the day because the sun is barely peeking over the horizon and the array cells are pointing mostly straight up. We also have an Mppt efficiency model, which we can take a look at here. We worked with our Mppt manufacturer to go ahead and sort of gather these curves of how the maximum power point trackers on our car actually perform when they serve their important function of converting the voltage produced by the array to the voltage produced by the battery in order to charge the battery and power our motors. So my actual model was created via a 4D hyperplane fit due to the fact that we have to take into account not only the input current and input voltage, but also the output voltage of the Mppt when determining how efficient it will be, as can be seen in the chart in the center. The actual hyperplane model I used was selected via the Akaike information criterion, and then verified via corrected AIC, as well as the cumulative variation of the mean absolute error. And in essence, what those tools all do is help to pick out which model is going to be the best by essentially trying to maximize the amount of information that you retain without leading to wild craziness. As a very simple sort of visual demonstration, if you're trying to connect 2 points and you do it with a line, that's going to be a really good model of connecting the two of them. If you try to connect 3 points, now your line is going to be off of all of them. But if you use a parabola, which now has sort of a squared term, you're going to be able to go through all 3 of them. But then if you go and use a third variable and you get a cubic in there, then you're actually going to be going ahead and sort of missing all of your points and diverging wildly at either end because you have too many variables for what you're actually trying to model. You're essentially overcomplicating your model. And what the Akaike information criterion is trying to do is get as close as you can to a perfect fit without bringing in so many variables that your model becomes overcomplicated and starts to diverge at either end. My final R² value of the model is 0.9567, which is quite good. Looking at some preliminary results, we can see that for one specific array design that we tested, our example system efficiency was 18.61526%, which, well, that is a lot of percentage points. is necessary when you're trying to compare two different designs in which you may move, say, a row of cells by about 2 centimeters, and you're trying to see which one performs better. And the whole idea of this system is to allow you to go in and sort of make direct comparisons between different hypothetical array designs in order to get the best possible array design for a given aero body shape out the other side. The chart on the left shows our array losses in watts over the course of a race. And as you can see, as I mentioned, the cosine losses are quite large, particularly near the start and end of each day. That's the points where there's anything showing at all. Nights are, you're not bringing in solar energy at night. And so that's, again, largely because the sun is going to be off on the horizon and your solar cell is going to be pointing up. And so of the sunlight that reaches you, very little is actually able to be absorbed by the car. On the right, we have a histograph, which essentially takes that same chart on the left and just normalizes everything to, at that specific moment in time, what 100% is. So this shows us over the course of a race, what percentage of energy is lost to each of our different loss factors. So we can see, for example, when you start a day, you have a lot of cosine losses, but then when you're pointing, which are the spikes where the red and yellow shoot way up in the middle and end of a day, as well as a little bit at the very beginning, that's when we're going to be bringing in the most energy because we've stopped moving the car and pointed the array directly at the sun to bring in as much energy as possible. So our cosine losses are minimized, and sort of the flat line you can see across all of them is actually dictated by the fact that the car itself is curved. And so when you point the array directly at the sun, you're not actually pointing every individual cell directly at the sun. And so this helps us to get a really good idea of sort of how much energy we're losing to things like the overall curvature of the car, and allow us to make better judgment calls when designing an upcoming vehicle. In terms of our actual power, you can see that for this particular array, our average example sunny day power was about 687 watts. So on a sunny day, we'd expect on average to bring in about 687 watts for like just kind of over the course of the day. And so this tool allows us to go ahead and figure out, all right, if we're bringing in, I'm going to round up to about 700 watts, then we want to be putting down with a battery that is, say, 5 kilowatt hours in sum total from the start of the race. We can figure out how much power we can be expending on any given day in order to not drain our battery completely and end the day with sort of enough headroom to make sure that we're not going to have to stop at some point because we've run out of power over the course of the race. So this analysis is really critical to pretty much any decision the electrical team makes, because everything you're doing as an electrical team uses up power, and knowing how much you actually have coming in is critical. And this tool allows us to get a sort of real-time approximation of how much energy we can expect. As for future work, as this model is not anywhere close to being fully fleshed out and completely perfect, things can always be improved. I would first like to improve the thermal loss model to work dynamically, and I will be coming back as a graduate student, so I hope to continue my work with this model and be able to do that myself. In the long term, regardless of whether this is me or another member of the team, we would like to sort of include a bypass diode model to enable greater per cell shading analysis. In essence, when cells are shaded, they provide no power to the car, but since you have multiple cells in series, you have other cells that aren't shaded that are trying to provide power. And so you use diodes to essentially bypass the cells that are shaded. And so what we would like to do is bring in the ability to model that and the sort of the losses caused by skipping over those cells through diodes. I would also really appreciate if somebody with more knowledge of how Unity works could port the Unity shading simulator to MATLAB and create a fully integrated suite. As things stand right now, we sort of have to copy the files and drag them to a new folder, run the code, and then copy the files from there over to a different folder to run the next module's code. And being able to simply use a graphical user interface, for example, where you put in the CAD files and you get out all of the results would be very nice. It would also be fantastic to incorporate our battery and motor models in the far future to sort of get an entire electrical system simulation rather than just focusing on the array. And lastly, we plan to use test data from this upcoming summer to verify our sweet results and make sure that the numbers we're seeing in real life approximately line up with what the model is predicting. If they don't, we'd like to figure out why that is, make corrections and adjustments, and use the tool again in 2023. I would like to give some special thanks, in particular to Ian Bertram, who did all of the Unity programming for this project, as well as helped with all of the data that I used for the different race files. Ibrahim Syed, who actually created all of the race files with the data provided by Ian Bertram. Dominic Kirschbaum, who was one of the people working on our Siemens Nx array design. Gabriela Teodoro, who also helped with Siemens Nx array design. Bennett Mejia, who also helped with Siemens Nx array design. Sam Romano, who was our Siemens Nx aerobody design lead, and the University of Michigan Solar Car Team Aerodynamics Division, who helped with Siemens Nx aerobody design. Thank you very much for listening today. If you have any questions, I'm available at icstewar@umich.edu. I can try to get back with you as quick as I can. Thank you very much, and have a wonderful day.